Hi, I'm Aurélien Géron, and today I'm going to show you how to implement a capsule network using TensorFlow. In my previous video, I presented the key ideas behind capsule networks, a recently published neural net architecture. If you haven't seen this video, I encourage you to do so now. Today I will focus on the TensorFlow implementation. I wrote a Jupyter Notebook containing all the code and detailed explanations, and I published it on my GitHub account. As always, I'll put all the links in the video description below. So I encourage you to clone it and play with it. So it reaches over 99.4 accuracy on the test set, which is pretty good, considering it's a shallow network with just 2 capsule layers and a total of about 1,200 capsules. There's a lot of code in this notebook, so I won't go through every single line in this video, but I'll explain the main difficulties I came across, and hopefully this will be useful to you for other TensorFlow implementations, not just CapsNets. Okay, let's build a network. First, we need to feed the input images to the network, and that's our input layer. We implement it using a simple TensorFlow placeholder. The batch size is unspecified so that we can pass any number of images in each batch, in this example 5. Note that we directly send 28 by 28 pixel images with a single channel since the images are grayscale. Color images would typically have 3 channels for red, green, and blue. And that's it for the input layer. Next, let's build the primary capsule layer. For each digit in the batch, it will output 32 maps, each containing a 6 by 6 grid of 8-dimensional vectors. The capsules in this particular map seem to detect the start of a line segment. You can see that the output vectors are long in the locations where there's a start of a line, and the orientation of the 8D vector gives the pose parameters. In this case, I've represented the rotation angle, but the vector's 8-dimensional orientation would also capture things like the thickness of the line, the precise location of the start of the line relative to the cell in the 6 by 6 grid, and so on. The implementation is really straightforward. First, we define 2 regular convolutional layers. The input of the first layer is X, the placeholder that will contain the input images we will feed at runtime. The second layer takes the output of the first layer, of course, and we use the parameters specified in the paper. The second layer is configured to output 256 feature maps. Each feature map contains a 6 by 6 grid of scalars. We want a 6 by 6 grid of vectors instead, so we use TensorFlow's reshape function to get 32 maps of 8-dimensional vectors instead of 256 maps of scalars. In fact, since the primary capsules will be fully connected to the digit capsules, we can simply reshape to one long list of 1,152 output vectors. That's 32 times 6 times 6 for each instance in the batch. And the last step is to squash the vectors to ensure that their length is always between 0 and 1. For this, we use a homemade squash function. Here it is. This function implements the squash equation given in the paper. It squashes every vector in an array along the specified dimension, by default the last one. So as you can see, it involves a division by the norm of the vector. So there's a risk of a division by 0 if at least one of the vectors is a 0 vector. So you could just add a tiny epsilon value in the denominator and it would fix the division by 0 problem. However, you would still run into another issue. The norm of a vector has no defined gradients when the vector is 0. So if you just use TensorFlow's norm function to compute the norm in this equation, then if at least one of the vectors is 0, the gradients will be undefined. It will return nan, not a number. So as a result, when gradient descent updates the weights of our model, the weights will end up being undefined as well. The model would effectively be dead, and you don't want that. So the trick is to compute a safe approximation of the norm, shown in the equation on the right. And that's about it. That's all for the primary capsules. Apart from computing the norm safely, it was pretty straightforward. On to the next layer where all the complexity is, the digit capsules. There are just 10 of them, one for each digit, 0 to 9, and they output 16-dimensional vectors. In this particular example, you can see that the longest output vector is the one for digit 4. And again, its orientation in the 16-dimensional space gives information about the pose of this digit, its rotation, its thickness, its skew, its position, and so on. By the way, note that most of the position information in the first layer was encoded in the location of the active capsules in the 6x6 grid. So for example, if I shift the digit 4 slightly to the left in the input image, then different capsules in the first layer get activated. See? So the output of these first layer capsules only contains a local shift information relative to the position of the capsule in the 6x6 grid. But in the second capsule layer, the full position information is now encoded in the orientation of the output vector in 16-dimensional space. Okay, now let's see how to implement this layer. The first step is to compute the predicted output vectors. Since this second layer is fully connected to the first layer, we will compute one predicted output for each pair of first and second layer capsules. For example, using the output of the first primary capsule, we can predict the output vector of the first digit capsule. For this, we just use a transformation matrix W11, which will gradually be learned during training, and we multiply it by the output of the first layer capsule. This gives us U hat 11, which is the predicted output of the first digit capsule based on the output of the first primary capsule. Since the primary capsules output 8-dimensional vectors and the digit capsules output 16-dimensional vectors, the transformation matrix W11 must be a 16x8 matrix. Next, we try to predict the output of the second digit capsule, still based on the output of the first primary capsule. Note that we are using a different transformation matrix, W12. And we do the same for the third capsule, using W13, and so on for all the digit capsules. Then we move on to the second primary capsule, and we use its output to predict the output of the first digit capsule, and so on for all the digit capsules. Then we move on to the third primary capsule, we make 10 predictions, and so on. You get the picture. There are 1,152 primary capsules, multiply 6 by 6 by 32, and 10-digit capsules, so we end up with 11,520 predicted output vectors. Now, we could just compute them one by one, but it would be terribly inefficient. So let's see how we can get all the predicted output vectors in just one matmul operation. Now you know that TensorFlow matmul function lets you multiply two matrices, but you may not know that you can also use it to multiply many matrices in one shot. This will be incredibly efficient, especially if you are using a GPU card, because it will perform all the matrix multiplications in parallel in many different GPU threads. So here's how it works. Suppose A, B, C, D, E, F, and G, H, I, J, K, L are all matrices. You can put these matrices in two arrays, each with 2 rows and 3 columns, for example. So we have 2 dimensions for this 2x3 grid of matrices, and each matrix is 2-dimensional. So these arrays are 2 plus 2 equals 4-dimensional arrays. If you pass these arrays, these 4D arrays to matmul, it will perform an element-wise matrix multiplication. So the result will be this 4-dimensional array containing A multiplied by G here, and B multiplied by H here, and so on. So let's use this to compute all the predicted output vectors. We can create a first 4D array containing all the transformation matrices. There's 1 row per primary capsule and 1 column per digit capsule. The second array must contain the output vectors of each primary capsule. Then we just pass these 2 arrays to the matmul function, and it gives us the predicted output vectors for all the pairs of primary and digit capsules. Since we need to predict the outputs of all 10-digit capsules for each primary capsule, this array must contain 10 copies of the primary capsule's outputs. We will use the tile function to replicate the first column of output vectors 10 times. But there's one additional catch. We want to make these predictions for all the instances in the batch, not just one instance. So there's an additional dimension for the batch size. It turns out that the primary output vectors were already computed for every single instance. So the second array is fine. It already has this dimension. But we need to replicate the 4D array containing all the transformation matrices so that we end up with one copy per instance in the batch. Now, if you understand this, then the code should be pretty clear. First, we create a variable containing all the transformation matrices. It has one row per primary capsule, one column per digit capsule, and it contains 16 by 8 matrices. That's 4 dimensions, and we add another dimension at the beginning of size 1 to make it easy to tile this array for each instance in the batch. Now, the variable is initialized randomly using a normal distribution of standard deviation 0.01. That's a hyperparameter you can tweak. And that's about it. We create this variable. Next, we want to tile this array for each instance. So first, we need to know the batch size. We don't actually know it at graph construction time. It will only be known when we run the graph. But we can use TensorFlow's shape function. It creates a tensor that will know the shape at runtime, and we grab its first dimension, which is the batch size. Then we simply tile our big W array along the first dimension to get one copy per instance. Now recall that the output of the primary capsules was a 3-dimensional array. The first dimension is the batch size that we will know at runtime. Then there's one row per capsule, and each capsule has 8 dimensions. So we need to reshape this array a bit to get the shape that we are looking for to do the big matmul operation. First, we add an extra dimension at the end using TensorFlow's expanddims function, and the vectors are now represented as column vectors instead of one-dimensional array. Each of these is a column vector. A column vector is a matrix, a 2D array with a single column. Then we add another dimension for the digit capsules. And we replicate all the output vectors 10 times across this new dimension, once per digit capsule. And lastly, we just use matmul to multiply the transformation matrices with the primary capsule's output vectors, and we get all the digit capsules' predicted outputs for each pair of primary and digit capsules and for each instance in the batch in one shot. And that's the end of the first step for computing the digit capsules' outputs. We now have a bunch of predicted output vectors. The second step is the routing by agreement algorithm. So first, we set all the routing weights to 0. For this, we just use TF zeros. There's one weight for each pair of primary and digit capsules and for each instance. The last 2 dimensions here are equal to 1. They will be useful in a minute. Next, we compute the softmax of each primary capsule's 10 raw routing weights. Okay, so softmax happens along this dimension. Next, we compute the weighted sum of all the predicted output vectors for each digit capsule using the routing weights. So the weighted sum is along this dimension. This is pretty straightforward TensorFlow code. First, multiply the routing weights and the predicted vectors. This is an element-wise multiplication, not a matrix multiplication. Then just compute the sum over the primary capsule dimension. And the 2 dimensions we added earlier for the routing weights are useful in the multiplication step so that the 2 arrays have the same number of dimensions, the same rank. They don't have the exact same shape, but they have compatible shapes, so TensorFlow will perform broadcasting. Now, if you don't know what broadcasting is, this should make it clear. I'm multiplying 2 matrices, but one of them just has 1 row, so TensorFlow will act as if this row were repeated the appropriate number of times. You could achieve the same thing using tiling as we did earlier, but this is more efficient. You may wonder why we didn't use broadcasting earlier, but the reason is it does not work for matrix multiplication. Here we're doing element-wise multiplication. Okay, back to the digit capsules. We computed a weighted sum of the predicted vectors for each digit capsule, and we just run the squash function, and we get the outputs of the digit capsules. Hooray! But wait, this is just the end of round 1 of the routing by agreement algorithm. Now on to round 2. So first, we need to measure how good each prediction was, and use this to update the routing weights. For example, look at the predictions that we made using this primary capsule's output. Notice that, for example, the prediction for digit 4 is excellent, and this is measured using the scalar product of the predicted output vector and the actual output vector. These two vectors are actually represented as column vectors, meaning a matrix with a single column. So to compute the scalar product, we must transpose the predicted column vector u hat ji to get a row vector, and multiply this row vector and the actual output vector vj, which is a column vector. We will get a 1-by-1 matrix containing the scalar product of the vectors. And now, of course, we need to do this for each predicted vector. So once again, we can use the matmul function to perform all the matrix multiplications in just one shot. First, we must use the tile function to get one copy of the actual output vectors vj for each primary capsule. Then we use matmul, telling it to transpose each matrix in the first array on the fly, and lo and behold, we get all the scalar products at once. So now we have a measure of agreement between each predicted vector and the actual output vector. We can then add these scalar products to the raw weights using a simple addition, and the rest of round 2 is exactly the same as the end of round 1. The code is really identical, except we're now using the raw routing weights of round 2. We compute their softmax to get the actual routing weights for round 2, then we compute the weighted sum of all the predicted vectors for each digit capsule, and finally we squash the results. And now we have the new digit capsule outputs, and we finish round 2. We could do a few more rounds exactly like this one, but I'll stop now and use the current output vectors at the end of round 2 as the output of the digit capsules. Now, you probably noticed that I implemented the routing algorithms loop without an actual loop. It's a bit like computing the sum of squares from 1 to 100 with this code. Of course, this will build a very big TensorFlow graph, but it works. You can think of it as an unrolled loop. Now, a cleaner way to do this would be to write a for loop in Python like this. Much better. However, it's important to understand that the resulting TensorFlow graph will be absolutely identical to the one produced by the previous code. All we're doing here is constructing a graph, and TensorFlow will not even know that we used a loop to build the graph. Again, this works fine. It's just that you end up with a very large graph. So you can think of this loop as a static loop that only runs at graph construction time. If you want a dynamic loop, one that TensorFlow itself will run, then you must use TensorFlow's while loop function like this. The while loop function takes 3 parameters. The first one is a function that must return a tensor that will determine whether the loop should go on or not at each iteration. The second parameter is also a function that must build the body of the loop, and that will also be evaluated at each iteration. And finally, the third parameter contains a list of tensors that will be sent to both the condition and loop body function at the first iteration. For the following iterations, these functions will receive the output of the loop body function. So you can pause the video if you need to take a closer look at this code. Once you get it, you can try modifying my CapsNet implementation to use a dynamic loop rather than a static unrolled loop. Apart from making the code cleaner and the graph smaller, using a dynamic loop allows you to change the number of iterations using the exact same model. Also, if you set the swap memory parameter of the while loop function, if you set it to true, TensorFlow will automatically swap the GPU memory to CPU memory when it can to save GPU memory. Since CPU RAM is much cheaper and abundant, this can really be useful. And that's it. We've computed the output of the digit capsules. Cool. Now the length of each output vector represents the probability that a digit of that class is present in the image. So let's compute these probabilities. For this, we cannot use TensorFlow's norm function because training will explode if there's a zero vector at any point, as I mentioned earlier. So instead, we used a homemade safe norm function, similar to what we did with the squash function. And note that the sum of the probabilities don't necessarily add up to 1 because we are not using a softmax layer. This makes it possible to detect multiple different digits in the same image, but they all have to be different digits. You can detect a 5 and a 3, but you cannot detect, say, 2 5s. Next, let's predict the most likely digit. We just used the argmax function that gives us the index of the highest probability. The index happens to be the number, the digit itself. Note that we first get a tensor that has a couple extra dimensions of size 1 at the end, so we get rid of them using the squeeze function. If we called squeeze without specifying the axes to remove, it would remove all dimensions of size 1. This would generally be okay, except if the batch size was equal to 1, in which case we would be left with a scalar value rather than an array, and we don't want that. So it's better to specify the axes. Great! Now we have a capsule network that can estimate class probabilities and make predictions. We can measure the model's accuracy on the batch by simply comparing the predictions and the labels. In this case, the prediction for the last digit in the batch is wrong. It's 7 instead of 1. So we get 80% accuracy. Now, the code is really straightforward. We just use the equal function to compare the labels and the predictions ypred, and this gives us an array of booleans. So we cast these booleans to floats, which gives us a bunch of zeros for bad predictions and ones for good predictions. And we compute the mean to get the batch accuracy. The labels y are just a regular placeholder, nothing special. And that's it. We have a full model able to make predictions. Now let's look at the training code. This diagram is about to get pretty crowded, so I'll remove the accuracy for clarity. And now first, we want to compute the margin loss. It's given by this equation. By the way, I made a mistake in my first video. I squared the norms instead of squaring the max operations. Sorry about that. This here is the correct equation. Computing it is pretty straightforward, so I won't go through it in details. The only trick is to understand how you can easily compute all the tk values. For a given instance, tk is equal to 1 if a digit of class k is present in the image, otherwise it's equal to 0. So you can get all the tk values for each instance by simply converting the labels to a one-hot representation. For example, if an instance label is 3, then for this instance, T will contain a 10-dimensional vector full of zeros except for a 1 at index 3. Okay, next we want to compute the reconstruction loss. So first, we must send the outputs of the digit capsules to a decoder that will try to use them to reconstruct the input images. This decoder is just a regular feed-forward neural net composed of 3 fully connected layers. It's really simple code, so you can pause the video if you want to take a close look at it. It outputs an array containing 784 values from 0 to 1 for each instance, representing the pixel intensities of 28 by 28 pixel images. And that's it. We have our reconstructed images. We can now compute the reconstruction loss. This is just the square difference between the input images and the reconstructions. Since the input images are 28 by 28 by 1, we first reshape them to 1 dimension per instance with 784 values each. Then we compute the squared difference. Now we can compute the final loss. It's just the sum of the margin loss and the reconstruction loss, scaled down to let the margin loss dominate the training. Pretty simple, as you can see. Now let's add the training operation. The paper mentions they use TensorFlow's implementation of the Atom optimizer using the default parameters, so let's do that. We create the optimizer and call its minimize method to get the training operation that will tweak the model parameters to minimize the loss. We're almost done, but there's one last detail I didn't mention in the first video. The paper indicates that the outputs of the digit capsules should all be masked out except for the ones corresponding to the target digit. So instead of sending the digit capsules outputs directly to the decoder, we want to apply a mask first, like this. The mask will have the same shape as the digit capsules output array, and it will be equal to 0 everywhere except for ones at the location of the target digits. By multiplying the digit capsules output and the mask, we get the input to the decoder. But there's one catch. This picture is good for training, but at test time, we won't have the labels. So instead, we will mask the output vectors using the predicted classes rather than labels, like this. Now, we could build a different graph for training and for testing, but it wouldn't be very convenient. So instead, let's build a condition operation. We will add a Boolean placeholder called mask with labels. If it is true, then we use the labels to build the mask. If it is false, then we use the prediction. Note the difference. Okay, and here's the code. We build the mask with labels placeholder, which will default to false so that we only need to set it during training. And then we define the reconstruction targets using TensorFlow's const function. It takes 3 arguments. The first one is a tensor representing the condition, in this case simply the mask with labels placeholder. The second parameter is a function that returns the tensor to use if the condition is true, and the third parameter is a function that returns the tensor to use if the condition is false. Then to build the mask, we simply use the onehot function. Now there's actually one slight problem with this implementation, and to explain it, I need to step back for a second and talk about how TensorFlow evaluates a tensor. Suppose we built this graph. These are all TensorFlow operations, and we want to evaluate the output of operation A. The first thing TensorFlow will do is resolve the dependencies. It will find all the operations that A depends on directly or indirectly by traversing the graph backwards. In this case, it will find C, D, and F. Next, it will run any of these operations that has no inputs. These are called root nodes, in this case F. Once F is evaluated, operations C and D now have all the inputs they need, so they can be evaluated, and TensorFlow will actually try to run them in parallel. Say D finishes first, A still has one unevaluated input, so it can't run yet, but as soon as C is finished, A can be evaluated, and once it's done, the eval method returns the result and we're good. You can actually evaluate multiple operations at once, for example, A and E, and the process is really the same. It finds all the dependencies, runs the root operations, and then goes upward, running every operation whose inputs are satisfied. And once it's got both the values for A and E, it returns the results. So let's apply this to our reconstruction targets. This tensor is the output of the const operation, which has 3 parameters, masked with labels, a function that returns y, and a function that returns ypred. And when we evaluate the reconstruction targets, or any tensor that depends on it, such as the final loss, which depends on the reconstruction loss, which eventually depends on the reconstruction targets, well, what happens is, as earlier, TensorFlow starts by resolving the dependencies. It finds all 3 bottom nodes, and it evaluates them all. So ypred may finish first. Since these operations are run in parallel, there's no way to know in which order they will finish. So, y may finish next. And finally, mask with label finishes. So suppose it evaluates to true. Now the reconstruction targets has all the inputs it needs, so it can be evaluated. And of course, it does the right thing. Since mask with labels is true, it returns the value of y, which is good. But notice that ypred was evaluated for nothing. We're not using its output. It's not a big deal, since during training we need to evaluate the margin loss, which depends on the estimated class probabilities, which is just one step away from the prediction. So computing the predictions won't add much overhead. But still, it's a bit unfortunate. Now suppose mask with labels evaluates to false. Then again, the reconstruction targets will do the right thing. It will output the value of ypred. But this time, we evaluated y for nothing. It's just a placeholder, so it won't add much computation time, but it means that we must feed y even if mask with labels is false. Well, actually, we can just pass an empty array, and that's fine. So it will work, but it's kind of ugly. So this unfortunate situation is due to the fact that the functions we passed to the const function do not actually create any tensor. They just return tensors that were created outside of these functions. So if you build tensors within these functions, then TensorFlow will do what you expect. It will stitch together the partial graphs created within these functions into a graph that will properly handle the dependencies. So you might be able to modify my code and fix this ugliness. I tried, but I ended up with pretty convoluted code, so I decided to stick with this implementation. I hope it won't keep you awake at night. So we've actually finished. Here's the full picture again. The construction phase is over. Our graph is built. Now on to the execution phase. Let's run this graph. First, let's look at the training code. It's really completely standard. You create a session. If a checkpoint file exists, load it, or else initialize all the variables. Then run the main training loop for a number of epochs. And for each epoch, run enough iterations to go through the full training set. And inside this loop, we simply evaluate the training operation and the loss on the next batch. We feed the images and the labels of the current training batch, and we set mask with labels to true. That's pretty much all there is to it. In the notebook, I also added a simple implementation of early stopping, and I print out the progress, plus I evaluate the model on the validation set at the end of each epoch. But the most important part is here. After training, I just run a few test images through the network and get the predictions and reconstructions. As you can see, the predictions are all correct, and the reconstructions are pretty good. They're pretty close to the original images, except that they're slightly fuzzier, as you can see. Here's the code. There's really nothing special about it. I take a few images, I start a session and load the model. Then I just evaluate predictions, the predictions and the decoder's output. And I also get the capsules output so I can tweak them later. The ugliness I mentioned earlier is right here, right? I'm forced to pass an empty array. This value will be ignored anyway. And finally, the code tweaks the output vectors and passes the results to the decoder. So we can see what each of the 16 dimensions represent in the digit capsules output vector. For example, this image shows the reconstructions we get by tweaking the first parameter. So the notebook produces one such image for each of the 16 parameters. And as you can see, in the first, second, and last rows, we see that the digits become thinner and thinner, going to the right, or thicker and thicker to the left. So it holds information about thickness. And in the middle row, you can see that the bottom part of the number 5 gets lifted towards the top. So probably that's what this parameter does for this digit. Before I finish, I'd like to thank everyone who shared and commented on my first video. I really had no idea it would receive such an enthusiastic response, and I'm very grateful to all of you. It definitely motivates me to create more videos. If you want to learn more about machine learning and support this channel, check out my O'Reilly book, Hands-on Machine Learning with Scikit-Learn and TensorFlow. I leave the links in the video description. If you speak German, there's actually a German translation coming up for Christmas. And if you speak French, the translation is already available. It was split in 2 books, but it's really the same content. And that's all I had for today. I hope you enjoyed this video and that you learned a thing or two about TensorFlow and Capsule Networks. If you did, please like, share, comment, subscribe, and click on the bell icon next to the subscribe button to receive notifications when I upload new videos. See you next time.